Hello everybody, thank you for tuning in. My name is Logan Ebert. I'm a graduate student researcher at the University of California, Davis. In the summer of 2019, I was partnered with the Wisconsin Potato Vegetable Grower Association to study water stress in potatoes in the Central Sands region of Wisconsin. On the docket today, we will cover water issues in the Wisconsin Central Sands, mission planning and photogrammetry, the high-resolution mapping of evapotranspiration model surface temperature and phenological inputs, evapotranspiration outputs from the model, sources of air, and where we'll be going from here. The Central Sands gets its namesake from the high sand content soil left over from glacial outwash in the last ice age. This region is also home to a large portion of Wisconsin's high-capacity wells. A high-capacity well in Wisconsin is any that pumps more than 100,000 gallons per day. Most of these wells are for irrigated agriculture. The main crop grown in this region are potatoes, field and sweet corn, soybeans, and sweet peas. The over-extraction of groundwater from these systems has caused issues with groundwater-fed streams in the area, as well as drying up of shallow private wells. The Central Sands' high agricultural presence and its highly permeable soils has led to issues of nitrate leaching and accumulation in groundwater. This has become problematic for both the environment and private well owners who now have to pay for the additional filtration of their water. Our research goals for this project were to adapt the high-resolution mapping of evapotranspiration model for low-altitude drone flights, to investigate the need for atmospheric correction at different elevations with the drone, and to evaluate the influence of capture elevation on modeled ET values. We coordinated with the grower to avoid days that were either unfavorable or unsafe. For example, when the irrigator was running or when the crop duster was flying overhead. We decided to use the drone to collect remotely sensed data of the field. 6 bands were collected: red, green, blue, near-infrared, infrared, and thermal. 8 flight series were conducted over the growing season with 3 flights. One at 90 meters, one at 60 meters, and the final at 30 meters height. These heights were picked around the limits of the drone. 90 meters is near the highest a drone can be legally flown in this situation, and 30 meters is the lowest that we could efficiently fly. 60 meters was selected as a middle ground. The rest of our data was collected at a nearby meteorological station. The raw photos collected were mosaicked using AGSOS Metashape, and the post-processing and ET modeling was done using R's raster package. This 225-acre potato field was our test site. A 1-hectare subsection surrounding an Eddy flux tower was the focus of our study. We chose this subsection because it covered the domain of the Eddy flux tower while allowing us to conserve the battery charge we needed to fly the 3 flights. The field uses a center pivot irrigation system, centered at this circle. Bisecting our subsection is a field road used to access the center pivot and other duties on the farm. We used AGSOS Metashape to convert the collection of raw images into usable rasters. The thermal band simply had to be converted from centikelvin to degrees Celsius. The other bands needed to be converted from a digital number to reflectance values using relationships provided by the camera manufacturer. Part of the processing of the multispectral bands included the calibration of the reflectance values using images of a reflectance calibration panel from before and after each flight. The bands then needed to be aggregated to 5 meters to calculate the enhanced vegetation index values. Then known relationships were used to convert those values into canopy height and leaf area index rasters. After that, the raster is then disaggregated to the resolution of the thermal band. We used the high-resolution mapping of evapotranspiration or Hermit model to calculate ET across our flight domain. Hermit is an energy balance-based ET model. The 3 main data inputs are meteorological data, a surface temperature raster, and an enhanced vegetation index, or EVI raster. The Hermit model uses an iterative process to narrow down sensible heat flux. Because of this, we were able to avoid the issues around the hot and cold pixel. This model has been validated and calibrated for potatoes in this region for airplane imagery. More information on the Hermit model can be found on GitHub. 5 of the 8 flight missions were selected for initial processing. These plots go in chronological order from left to right and decrease in elevation from highest to lowest. I would like to address the 30-meter August 6th flight. On that particular day, the drone went through the battery faster than expected, and part of the eastern edge was missed. there doesn't appear to be much change to the overall value range of surface temperature with the change in height. However, there is increased differentiation of soil versus cropped areas, best outlined by the difference in July 8th's 90 and 30 meter plots. And you can see the field row bisecting the field plot with the higher temperature range. Across these flights, ground spot check data was collected at 4 locations following the flights. 3 of the points were located in a cropped area, and the other one was on bare soil. We compared these values to address the need for atmospheric correction. Across these elevations, the 90 meter flight had the best R-squared value, and the 30 meter had the lowest root mean square error. However, when the 30 meter R-squared value is looked at, the fit is not reliable. Some discrepancies in this can be explained by the fact that the ground truth values were collected at the end of the flight series. This means that the time change from the start of the first flight to when we took a measurement was around half an hour apart. We took multiple measurements at each spot using an infrared thermometer. The thermometer was a fairly old model, and our collection method was not as consistent as we would have hoped for. We have since changed our methods to be more consistent and now have a newer thermometer. Surface temperature is one of the most important influences on the outcome of the Hermit model. However, for initial processing, we have decided to not correct the thermal values. Rather, we will use the error down the line in uncertainty calculations of the outputted ET values. The Enhanced Vegetation Index, or EVI, is a vegetation index that uses near-infrared, red, and blue bands to detect vegetation signals. We chose this over the Normalized Difference Vegetation Index, NDVI, because NDVI has an issue with becoming saturated with high chlorophyll presence. This was important to us because potatoes can reach high crop density and would make NDVI values unreliable. Like with surface temperature, EVI tended to have better differentiation of soil and crop in lower altitude flights. Since EVI uses multispectral data, it is prone to the influences of cloud interference. This can be seen on the 30 meter August 6 flight, where the left half was clouded and the right was not. A dark spot in the lower left-hand side of the plot can clearly be seen in the earlier plots. This is a bare spot in the field that had accidentally not been planted. Later on in the season, it would fill in with weeds and become harder to detect. Leaf Area Index, or LAI, values were derived from EVI rasters using known relationships for potatoes. The plots get the brightest, signifying the highest LAI on August 2nd. After that, the plots start to get darker, which signify the potato crop's senescing. The left half of the August 6th 30 meter flight is being underestimated due to cloud cover previously mentioned about its low EVI values. Here are the actual ET values put out by Hermit. Across all plots, the lowest ET areas are the field road that bisects the plot and the bare spot in the lower left-hand corner. Again, there's not a huge change in value with the change in elevation, but there tends to be better soil crop separation with the 30 meter flights. We then normalize the ET across the plot to create relative ET. We used the 5th and the 95th percentile values to avoid using outlier points that did not reflect the reasonable range in the field. This offers an intuitive illustration of where the largest stress is in the field and allows for comparison of flights from different points in the season. These are the plots of relative ET across the domain. The higher or brighter the value, the higher the rate of ET in that area. There seems to be a trend where there is the greatest variation in the field later in the season when the canopy starts to open up again. Looking back at the 30 meter August 6th flight, there appears to be a trend where the left-hand side of the plot has less relative ET. Since this isn't a general trend with the rest of the plots, I would assume that the influence of the cloud cover has underestimated ET in that area. There is also an unusually low spot in the upper left-hand corner of the 60 meter July 8th flight. I'm not 100% sure, but I hypothesize that this is due to vignetting of the thermal layer. If you have any idea, please let me know. Here we have the 30-minute ET values from the Eddy flux tower for our field season. An average of the Hermit ET value across the Eddy flux domain was taken for each flight and overlaid on this graph. Initially, it's great to see that our modeled values appear to fall close to the Eddy flux values. There doesn't seem to be much of a trend when it comes to the elevation, except that the 90 meter flight always had the highest values. Going on a day-to-day basis, we can see how the modeled values stack up to the Eddy flux values. On July 8th, the modeled values from all elevations fall within each other's standard deviation. The model values are also significantly higher than the Eddy values at the same time. On July 22nd, the model values still fall within each other's standard deviation. However, the model values are almost on the eddy flux curve. On August 2nd, the model values continue to fall within each other's standard deviation. The model values fall close to the eddy flux curve. On August 6th, the model values still fall within each other's standard deviation. However, the model values are coming out as higher than the eddy flux values. Lastly, on August 9th, we have the greatest separation between modeled values. The 60 and 30 meter flights came out nearly the same, while the 90 meter flight was reported as being on the higher edge of their standard deviation. All the flights still fall close to the eddy flux curve. There are many potential sources of error when modeling ET using drones or otherwise. Discrepancies between the drone data and the ground truth signify error from atmospheric interference, and in particular wind speed and variation. All the flights were flown below the tolerable wind speed, but every flight was different and the effects of gusting is hard to pinpoint on the domain. Cloud cover is an issue in the Midwest during the growing season. Ideally, the flights would be flown in clear conditions, but sometimes we had to fly during partially cloudy conditions. The shadow cast by clouds keys multispectral data. The meteorological inputs for Hermit have internalized air, which then gets added to the overall air of the model. We aim to quantify these values for uncertainty calculations down the line. It is difficult at this time to come to a definitive conclusion on what the best elevation to collect data is. However, I think it's important to consider the limitation of the drone systems. The lower you fly, the longer the flight is, and the more battery you require. From a wide-scale application point of view, the benefits of lower elevation would have to be significant to offset this cost of time and energy. It also depends on the irrigation goals and technology. While flying lower gives you the higher resolution data, if the irrigation system can't irrigate to that precision, there really is no need to have that higher resolution. With our camera system, we had about a 50 centimeter pixel for 90 meter flights. Since the field used a center pivot irrigator, there was no real need to have any higher resolution than that. This would be the same for pretty much all annual crops. But for perennial crops that will be invested in for a couple decades, it'd be more important to have higher resolution imagery. Going forward, we aim to run the rest of the flights for the 2019 Wisconsin Potato Series. After that, we will use the Monte Carlo approach to take the error from our input data and calculate uncertainty of our modeled ET values. And with that, do further study into the need of atmospheric correction for the images. But beyond that, we aim to adapt the Hermit model for other crops, including perennials as well as for Mediterranean climates. I would also like to see what other information we can get out of these collected images. I would lastly like to thank Heartland Farms for letting us use their land for the research and the following people for their help on this presentation. If you have any questions or suggestions, feel free to contact me. Thank you.